Okay. So here's the most recent standings. Disco has slid into third place. Although you can see down here, it's very close at the top. And indeed, Rack Shack and Ratatouille are not too far behind. Rack and Roll took a big fall this week. Rack Shack, probably that's the biggest move in a few weeks. All the way from 10th up to 4th.
But you're not gonna watch.
Hey, Ellie Chrisman, you're not muted.
Take your time, just switch it over.
Wait.
Hello?
Sorry.
Okay. All right, where was I? Oh, well, CD's nuts. No doubt, due to their name, is now way behind. Although, unlike some years where teams actually lost money, they are above $1 million. All right, so here's just. Okay. So here are the assets over time. Kind of see there's a top group, a middle group, and a bottom group. All right, here are sales versus price. So the red diamonds are this most recent period. These little orange hash marks are last period. And the blue pluses are the period before. So you can see that prices continue to fall. For the first time, we have several prices below $20. I find this really interesting. It looks pretty much the same every year, so it's kind of cool. This is sales versus price divided out by teams. So each different symbol represents a different team. I looked these guys up. Ones with the super low prices, that's the big three. If anyone's interested, apparently some team, I don't even know who this is, set unusually high prices for whatever reason. Just to check, I mean, stock price versus assets. Assets is not the sole predictor of stock price, but it's pretty good predictor. Although for the same number of assets, you can see that there can be a range of stock prices. So there are other factors that affect stock price, obviously. So interestingly, even though Disco fell into third place, they had a huge increase in their stock price. Stack and Rack's also doing pretty good. So this is the holdings page. In other words, it's showing the equity holdings the teams have in other teams. In other words, they subtract out the equity holdings they have in themselves. So there's at least 4 teams who hold over $100,000 in equity in other teams. And note that could be long or short. And in the past week, Crackheads seems to have invested heavily in other teams. The difference being over $42,000. Disco also put in 14. Well, I missed these guys here too. Rack It Up has a difference of 40, 45, 46,000. Okay. Some teams, Rack Mamba has a pretty low total investment, so as does Ratatouille. They're making their money the old-fashioned way. They earn it, as the old saw goes. Let's see, here's the industry report. CDs nuts, lowest on cash. Rack It Up has the most cash. Equity holdings range from over 60, I'm sorry, over 600,000 to around 360,000. As far as plants go, everybody seems to have about the same, except Rack It Up and Rack Mamba have less invested in plants. On the other hand, Rack Mamba and Rack 2 Duff Future have a lot more invested in warehouses than other teams. Finished goods inventory last week, every single team had finished goods inventory. Now 2 teams, Crackheads and Rack Mamba, have no finished goods inventory. Racks on Racks has lots of finished goods inventory. I guess that accounts for the name of their team. Current stock prices range from almost $25 to almost $15. Huge difference now. Earnings per share, only one team was over $1, and that was $1.01. And 4 teams had negative earnings per share. Not like the good old days when some teams were making over $2 a share. Pending dividends, there's a couple teams have good sized dividends. Stacking Racks has a smaller one, and then nobody else is paying any dividends. Insider holdings, Rack Shack, oops, sorry about that. Rack Shack continues to invest in themselves. Hold on a sec, I apologize for that. Yeah, continues to invest in themselves. They have the highest investment already. Come on. Where is my cursor? There it is. And they're investing even more next period. Okay, so they have a relatively low amount of cash, but not, not nothing. Unlike Rack It Up, who is again sitting on over $500,000 stored underneath their mattress. All right, here's sales from last week. 4 teams sold well over 10,000 units. 1 team sold under 4,000. And then from in between, things varied quite a bit. Oh, this is wrong. That's from last week, so that's nothing. All right, that is it for our review of the game. Does anyone have any questions? Thank you guys for turning your camera on. I appreciate it. It's also a very festive environment. There we go. Nothing like talking to a wall. Well, thanks to the 6 more of you who got the hint. All right, so today's lecture is about quality. But before we get to that, just kind of remind you or update you on what the schedule is for the rest of the class. So this is today, we're going to talk about quality. This is the week where we have 2 decisions. So you have decisions that are due tomorrow. All right, period 9. Decisions due tomorrow at 6 p.m. and then again Monday at 6 p.m. So we will not have class. There will be 2 decisions between this week and next week's class. So don't forget. Okay. Then Wednesday, next Wednesday, we're gonna talk about scheduling and some of the things that I find very interesting in particular. So this is one of my favorite lectures. Quality, one of my least favorite, by the way. And then the following Wednesday is Thanksgiving week, so there's no class. But there will be decisions due the Monday before Thanksgiving. And then after you get back from Thanksgiving, again, there will be decisions due Monday, November 29th. Okay, the last day of class is December 1st. You may recall we're doing final presentations. Each group will make a presentation. And I'm going to talk a little bit more about final presentations now. Okay. So because every team is making a presentation, we're targeting them to be at about 10 minutes per team. We're going to use up most of the allotted one. It's not, sorry, my time is wrong here. It's 1:35 to 4:15 time slot. And we'll probably finish a little bit before the end of it, but we'll take up most of the class with presentation. And the order of presentation will be the last place team talks first and the first place team talks last. Okay, so we have time for a maximum of 15 minutes per team per presentation, but with changeover times and stuff like that, probably ought to target it more like 10 minutes and leave a little bit of time for questions from anybody, but in particular myself and Suchil. Here's what I would like to be in your presentation. Talk about the strategies you had that you used in the game, including what seemed to work well for you, if anything, and what didn't work for you, what went wrong, okay? Second thing I would like to see is I would like you to talk about the analytics you developed to help you make your decisions. If your answer is we just did everything by kind of pulling it out of the air, shall we say, that probably won't show very well in your presentation. Okay, so what tools did you develop, what analytics, and which of them were most useful? And finally, if you had to play the game all over again, what would you do differently? All right, so that's, and this is all, the presentation is this, the screens you're looking at now is all posted on the PowerPoint on course site if you want to go back and review this later. All right, I think I can just stop and see if anyone has any questions about the schedule of the presentations. Any questions? Okay. I'm not seeing any. Okay, so today's lecture is on quality management and quality control. I mentioned at the beginning of the semester how you guys don't have to take supply chain management 186, I think the number is, because this class substitutes for it. And in order to make that happen, to get the business school to agree to that, I had to include some topics in this class that I probably wouldn't otherwise have. This is one of them, quality management and quality control. For an engineer like myself, this is a little bit, what's the word I'm looking for, fluffy. Although at the end, the statistical process control is quantitative and actually something I actually know quite a bit about, believe it or not. Nevertheless, this probably is not the most interesting topic in the world. Some of it you, I'm sure, have heard about and know about, so let's just go through it. Okay, why is my, there we go. All right, there are several different sort of, let's call them management philosophies that are used out in the world of business.
We can see your screen, Professor Storr.
You can't see my screen. What happened? Oh, my computer is messed up. Okay, let's try again. Share screen. How long have you not seen it? When I was talking about the presentations, did you see?
Yeah, we saw the schedule. Okay, now we are seeing the quality management.
Okay.
Yes, we saw the schedule, Thanksgiving, etc. But yeah.
Okay. You can see this now?
Yep.
Okay. So there are several management philosophies that are just considered, quality management methods. You may have heard of some of them: total quality management, continuous quality improvement, Six Sigma, Lean. These are some of the most well-known ones. It's interesting how, at least in some quarters, these philosophies achieve what I call almost a religious level of true believers. The basic precepts of all of these things are quite similar, although there's some differences. We'll talk about them. So we'll talk about these quality management methods, and then the second part, we'll talk about statistical process control, which is a little bit more quantitative and less soft. So total quality management is probably the first one to come along, often abbreviated TQM. I should go ahead. Okay, so TQM was pioneered by a guy who is by now very famous, named W. Edwards Deming. Interestingly, he got his career, the start of his career was at the Bell Labs factory that is now closed down, but it's on Union Boulevard over in Allentown. So he worked for Bell Labs for a while, and then he moved to Japan. And while in Japan, he basically revolutionized the whole of industry in the whole country of Japan. The Japanese themselves credit him single-handedly turning around their whole industrial world. When I was a teenager, made in Japan was synonymous with poor quality crap. Within 25 years, it was the exact opposite was true. Japan made the highest quality cars, highest quality electronics, etc. And to this day, that is still the case. There is something in Japan called the Deming Prize. It's probably the most prestigious prize one can win in Japan. It's given out yearly to organizations that were particularly successful. I can back up a little bit. TQM is based on some basic principles that are hard to argue with. It's customer focused. You need to understand what your customer wants and needs, and then meeting or exceeding their expectations. It's based on the idea of having a foolproof process, if you will, and monitoring the process to make sure that it's working well, and also to monitor it, to provide information in a feedback sense to try and improve it. Benchmarking is also part of their idea here. Okay, so it's a customer-focused, long-term process, or kind of management philosophy. And it also relies on everyone in the organization to be focused along these dimensions. Right, the best way to understand Deming's ideas was that he has his 14 key points to increasing quality and productivity. And I will not I listed all 14 of them. I'll just spend a little time to talk about a couple of them. This one here, cease dependence on inspection to achieve quality. It's kind of interesting. Before Deming, the industry's view on quality was quite different. They basically viewed the ways to improve quality. There were kind of two things you could do to improve quality. One is to increase the quality of the materials and parts and things you used. And the other was to increase the level of inspection that you performed on your products. Note that both of those cost money. Deming believed that this was exactly the wrong philosophy, as we'll see in a minute. Another thing, another idea of Deming's, which actually is sort of out of favor nowadays, was that he suggested that you work with a single supplier. So you single source everything rather than dealing with multiple suppliers. His idea that you would pick these key suppliers and work with them closely to streamline the process and the interfaces between them and you. This is out of favor now, though, because it's also very risky, right? So, I mean, if your single supplier happens to be in the path of a big hurricane, this can be a big problem. Deming believed in improving constantly. So he was really the first to kind of trumpet this idea of constant process improvement. So I guess I should have mentioned when this was. This was back in, I think, the 50s and early 60s when this was kind of coming about. So drive out fear. So basically by this, he means that he wants all of the workers, all of the employees to have a stake in quality. And if they observe something going wrong, they should speak up. It was a common thing where, like, if you made a mistake and created a defect in some product that was rolling down the line, you kept your mouth shut, otherwise, because you'd be in big trouble, right? So he wanted the opposite of that to be the case. Eliminate slogans, exhortations, and targets for the workforce. I remember this when there was a time, maybe a decade ago, when Ford Motor Company had a slogan and they advertised it constantly, and it was "Quality is job one," and they would show how they had these giant signs hung up in all of their factories that said "Quality is job one." So, I mean, if you think about it, is that going to improve quality, putting up a big sign? That doesn't seem to make much sense. And indeed, it probably doesn't. Okay. So Deming was very focused on the employees of the company. He wanted them to be constantly educated and trained so that they would get better and better at doing their job. So again, it's a very employee and customer oriented viewpoint or management philosophy, shall we say. It's kind of like it's that the manager's job is to make the worker's job easier and better. Now, the key thing is that Deming, his idea was that improving quality reduces cost rather than increasing it. So Deming's idea was to make fewer defective products, right? By making fewer rejected products, having fewer returns from the customers, having fewer unhappy customers, reduces cost rather than increasing it. And then, as I mentioned before, prior to Deming, it was widely believed that the way to achieve higher quality was more expensive materials, fancier designs, and more inspections to make sure that things that went out the door were good. Okay, so all of these things down here, expensive materials, more inspections, cost money. If you improve your process so it makes fewer bad things, fewer rejects, that saves money and makes the customer happier. So, I mean, it may seem like kind of an obvious idea, but at the time it was actually kind of revolutionary. Okay, I don't know, these, like I say, these things, they're kind of faddish in nature. At some point, TQM went out of style and people just started calling it quality management rather than TQM, but I guess that's not a big deal. All right, so kind of an offshoot or the next generation of this was continuous quality improvement. It was based on, that was in Deming's things, but it was, only a part of it. This is like the idea is to actively seek out to improve your process. So, I mean, the basic idea was you say, okay, here's a process we could probably stand to improve. Let's study it carefully. Let's monitor what's going on, and let's think about ways to improve it. Then we'll design a better process, implement our design, and then continue to monitor and evaluate the process to assure it continues to work better as it was supposed to. And then hopefully, you can spread this throughout the organization. But the basic idea is active attempt to improve your process. Six Sigma is probably one you've heard of. I believe if you had IBE250, Professor Titus talks about it. It's focused on reducing process variability and errors. It has a very strange top-down deployment and structured roles, and we'll talk about this business in a minute. So where does the name Six Sigma come from? So you imagine if you have specification limits on a product, like say you're making a drive shaft and the diameter of that shaft is supposed to be a certain diameter. But if you're a mechanical engineer, you'll know that they usually put specification limits on it, which basically mean if the diameter is between the lower spec limit and the upper spec limit, then the process should be functionally fine. So Six Sigma says that you want to reduce your process variability. So, I mean, this here, the normal distribution curve represents the diameter of shafts you're producing. Since variability is natural in any process, the shafts will not all be exactly the same dimension. So there is natural variability. And if you can reduce the variability such that the variability is plus or minus 6 standard deviations from the spec limit, then you can see that pretty much every single one will fall well within the spec limits. So that's where the name Six Sigma comes from. So imagine an implementation of this, filling bottles of soda, right? So the way this would work is you know, on the label, the bottle says 12 ounces of soda, right? And so when you fill it, every bottle is gonna have a different amount of soda in it. It'll be a random variable. But depending on the variability, oh, and I should say this, you wanna make sure you get at least 12 ounces in with high probability, because if you don't have more than 12 ounces with high probability, you'll get in big trouble with the government who monitors these things. So think about this. If you want to make sure that, say, 95% of your bottles have 12 ounces or more. So this is our 5% tail here. This is our 5% tail here. If your process is highly variable, you have to set the mean much higher than if the process variability is low. So you can think about it as this red double-sided arrow represents how much extra soda you have to give away in each bottle because of the process variability. Obviously, the more variability, the more free soda you have to give away and the more money you have to spend. So this is basically showing one way of thinking about how process variability is directly related to cost. Okay, so Six Sigma was made really popular by two companies, General Electric and Motorola, who were doing this in probably the 80s was the peak of them talking about Six Sigma. So again, they focus on this idea of quality and defects being measured in terms of deviation or variability, and they attempt to reduce process variability. They have strategies to eliminate defects and reduce process variability that we'll talk about in a minute. But then they have this weird structure of this top-down deployment where you have master black belts who train black belts, who train green belts, who train yellow belts. The yellow belts are the ones who are down there on the, say, on the factory floor, trying to implement these ideas and improve processes. So it's a very top-down hierarchical approach. Which I think is kind of goofy. Let's just say that. Okay, so they have these frameworks. Okay, so when you're improving a system, how do you improve a system? Well, first you define the problem, you measure the process, you analyze the results, you improve the system, and then you implement controls or monitoring on the system to ensure that it continues to operate as perceived. I don't know what else to say about this other than duh. I mean, yeah, it's kind of, that's what you would do, isn't it? I don't know. They have these various statistical tools that they use. We'll talk more about them in a minute. Suffice it to say, they're very basic statistical tools that they utilize in the process improvement process. Okay. So a lot of times we're trying to re-engineer processes to make them better. And there's kind of two tools involved here. On the bottom, we have these tools used to measure and display findings about the process. That's these guys here on the previous page. And there are methods for generating new ideas, like the 5W2H approach. God, I feel like I'm in the business college. What, why, where, when, who, how much. Methods for generating new ideas. Brainstorming. Wow, there's a crazy thought. How about this one? Interviewing, or as I like to call it, talking to people. Although interestingly, talking to people is a really good approach. When I started at Lehigh, we had an old guy in our department named Wally Richardson. Wally was actually pretty famous. His advisor in graduate school is actually Lillian Gilbreth. If you know who Lillian Gilbreth is, she is the founder of the field of industrial engineering. And also famous for writing a very popular book called Cheaper by the Dozen. Wally made a lot of money consulting. He was really good at walking into a factory and figuring out what was wrong. And he told me a story once about how he walked into a factory that made pasta. And they had a bunch of chemical engineers working there. And I said, geez, Wally, we have a problem. We put in a bunch of flour and water and eggs on one end of the process. So if we put in 10 pounds of stuff going in, we only get 9 pounds coming out. And we don't understand it because we thought mass was supposed to be conserved. So I said, okay, I'll go take a look, right? So he just walks around the plant, starts talking to people. Finally, he's talking to this one guy and he says, hey, you know, put in 10 pounds, I only get 9 pounds out. So you know anything about that? And the guy said, oh, sure. And he says, come over here. And he goes to this big giant machine that has this big door on the bottom of it. And he opened the door and there's a giant pile of pasta sitting there on the floor. Right? So, I mean, well, I don't know how much money he made for that, probably a ton. And it just shows the value of talking to people. So, well, I'm not sure this is something we need to teach in a college class. Maybe it is. The idea of talking to people is a really good idea. I think Professor Costa would agree with me on that. And there are all these things that make my head spin. Structured ways to talk to people. Let's call them that. Focus groups, another structured way to talk to people. I guess the emphasis here is picking people that know something to talk to, or a representative of those you want to learn something about, and then benchmarking. So it's like, you know, compare your process to the best practices of other companies, which is a great idea if your competitors are willing to let you in and show you all of their best ideas, which seems unlikely, at least in any kind of a competitive market. But it's something that we in colleges do, right? We benchmark against other industrial engineering departments and things like that. Famous idea they use in Japan a lot, called Kaizen teams, or over here we tend to call them quality circles. So this is going back to the idea where every employee is supposed to be involved in and responsible for the quality of products. The idea here is basically you form groups of employees and have them meet every week or so and discuss ideas about quality and discuss ways to improve processes, discuss what's going wrong, and try and use these discussions to improve processes. The idea here, I think, is that those people who are doing the work, who are on the floor running the machines and making the products, have much greater insight than managers who, God knows what they do, but they don't know much about what's going on the floor. So we're trying to garner that information from the people that really know what's going on. All right, so we talked about these fancy statistical tools back here that we use in Six Sigma. So let's go through them. This is called a check sheet. So you notice how there are various defects that we're going to keep track of. And so each week we mark down how many they are. So I like to call this one counting. So a histogram, which basically amounts to counting and then plotting your counts. Scatter diagram. So this is, plotting two variables on one plot. This is by far the fanciest statistical tool involved in, or that they talk about. Flow charts. Okay. Fishbone diagrams, or cause and effect diagrams. These are ones you may or may not have heard about before. The idea is you identify a problem. In this case, patients are waiting too long. Perhaps they're waiting too long in the waiting room of the emergency department. And then you go back and you investigate, and then you start writing down the reasons or the causes of this problem, right? That's why it's a cause and effect diagram, excuse me. I mean, this is kind of useful, I guess. Often involves a lot of work because you have to go track down what's causing these problems. So the information you get from this is useful. I'm not sure the diagram itself is particularly profound. Pareto diagrams, it's like a histogram sorted by frequency. So this is showing the various quality issues sorted from most frequent to least frequent. So obviously this allows you to say which one's causing the biggest problem and maybe focusing your attention on those that are the biggest problem. So the Pareto diagram, Pareto, I think, said something to the effect that 20% of the problems cause 80% of the issues. Let me see. 20% of the quality problems responsible for 80% of the damage. I don't know, something like that. At any rate, allows you to focus on the most common problems. All right, so that is our review of Six Sigma. The last one, and probably the most recent one, is commonly known now as Lean, although it was originally known as the Toyota production system. The name implies these ideas came out of Toyota. It's also a continuous improvement focused management philosophy, but it's particularly focused on the idea of improvement by elimination of waste. It's more of a bottoms-up approach. They again believe in like organizing teams throughout the organization teams of employees, train them on the lean system, and then put them to work to improve the process and eliminate waste. So one thing in lean that I guess is kind of new is that you can create process maps. So imagine that each one of these dots is a step in a process. And then you can categorize each step as a value-added step, value-added activity, or non-value-added activity. And it's kind of natural to focus on the value-added steps, right? That's where the significant work is getting done. But the lean concept says you should rather focus on the non-value-added steps and basically try and get rid of as many, if not all, non-value-added steps as you can. Or as I like to call it, and I got an article from my friend, Dr. Thiemann. I wanted to show you this article. Where is it? This is from the New England Journal of Medicine. And we all laughed when we saw this because this is what I call a lean product. This is what I call lean. Getting rid of stupid stuff, right? It was actually in the New England Journal of Medicine. And I guess to some degree, all of this stuff can be kind of summarized that way, right? But particularly lean. Lean is stop doing stupid stuff. One of the reasons why these things are so simple is because so many organizations do so many stupid things. Things that cost money, that cause inefficiency, that cause poor quality and defects. And most organizations can make a lot of improvement by just stopping doing all of those stupid things. And to identify stupid things and stop doing them is not really rocket science most of the time. So there are very few organizations that or industries that are so sophisticated that there's not plenty of stupid things you could stop doing. Interestingly, I've studied many organizations in my time, or industries, and the one industry that does by far the most stupid things is healthcare. They are so far behind in terms of quality that it's scary. There's an article that came out, I don't know how long it was, 15 years ago. It was like the second leading cause of death was medical errors, mistakes made by healthcare providers, something like that, with hundreds of thousands of people dying every year because healthcare people made mistakes. And that's because they don't have rigorous, well-defined, monitored processes. Every healthcare provider does whatever the hell they want to. Maybe I'm exaggerating a little bit, but you get my point. Okay, I'm getting tired of all this management stuff. Tired. All right, so stop doing stupid stuff, get rid of wasteful stuff. I mean, there's all kinds of wastes, right? That's the guy who helped me with this lecture works for a hospital. So these are just examples of wastes in hospitals. I mean, yeah, it's kind of self-explanatory. Yeah, the average nurse walks about 6 miles every shift. Oh, gee, I don't want to talk about this stuff either. Okay, finally, the second part of the lecture. Something a little bit more quantitative, although this is not complicated quantitative stuff. It's actually fairly simple. This is called a statistical process control. And it's a way to measure and improve quality in a reactive sort of way. All right, so variability is endemic and inherent in any process. It's natural, right? And so when a process is operating as it is supposed to, it will still exhibit variation, right? Everything's working well, and yet the diameter of every shaft that comes off the production line is slightly different, etc. Well, that's each process has this kind of natural random variation in it, but it may exhibit, at least from time to time, non-random systematic variation that has some source, right? Think of it as being something went wrong to increase or change or make the process more variable or vary in unnatural ways. So when these systemic causes of variation occur, the idea is to find them, to detect them, find what caused them, and then prevent them from happening again. So statistical process control is designed as a very simple statistical technique designed to detect non-random variation, so that once it's detected, you can analyze it and hopefully fix the problem. So statistical process control is based on something called a control chart, whereas a control chart sets up control limits. These two darker lines here represent control limits that reflect the natural process variability. So when the process is behaving normally and exhibiting only natural random variation, it will vary pretty much always within these limits. You can think of these as like maybe the upper, the 99th percentile and the first percentile of the distribution of the quality measure that we're keeping track of. So you take sample, you collect data every so often, and you plot the outcomes over time. And if everything is remaining normal, the plots will vary between these control limits. But every now and then it might jump up high, and then you say, aha, something happened. That's not natural variation. That's the basic idea. So the idea is kind of like this. You figure out what is the distribution of the quality measure that you're interested in monitoring. And then you put the control limits at some upper, and basically out in the tails of the distribution. So that, some high percentage of the time, as long as the process is behaving naturally, you will be inside the control limits. Okay? So that's the basic idea. So there are basically 3 different kinds of charts, control charts we're going to learn. We're going to learn a C chart, which is for count type data or count type quality measures. A P chart, which is for percentage quality measures. Finally, X bar and R charts, which are for continuous variable type quality measures. All right, so these C charts I use, as I said, for like numbers or counts. So your quality measure, for example, could be the number of defects on a silicon wafer, the number of medication errors per week in a hospital, the number of surface defects in a sheet of steel. You get the idea, it's the number of things. And typically, if you've studied a little bit of probability statistics, count data can typically be modeled using a Poisson distribution. And so we would use the Poisson distribution to establish the control limits. So here's a simple example. We have 2 years or 24 months worth of data. So each month we count the number of infections that were observed in patients in an intensive care unit. All right, So you can see it varies each month. So we take the average over all of these months, and the average turns out to be 4. So if you recall the Poisson distribution, the Poisson distribution has a mean, and the mean and the variance are equal. It has a single parameter, often called lambda, and the mean of the Poisson is lambda, and the variance of the Poisson is lambda. So we'll use the average to estimate the mean. And then the standard deviation would be the square root of the variance. The variance is also 4. And we're going to put our control limits, in this case, at the mean plus and minus 2 standard deviations. Some people use 2, some people use 3. It's kind of arbitrary. I'm going to use 2. So plus or minus 2 standard deviations. The mean, where's my cursor? The mean for plus or minus 2 times the standard deviation square root of 4. All right, so we build our control chart. We have the center line at our mean of 4. And our upper and lower control limits at the plus or minus 2 standard deviations. All right, now I plot the data from the previous page on the chart. And yes, everything seems to fall within the control limits. All right, so then we have this chart set up. We would then, as we go out into the future, off to the right, we would continue to count the number of infections in the ICU and plot it on this chart. And it may go up, it may go down, but if it ever ends up way up here at say 9, that is indicative that something in the process has changed, right? There's very low probability of getting 9 infections unless something has changed in the process. And that's what we're looking for. We're looking for what's changed, and then we can go figure out what caused that change. All right, so these control charts all work the same way. Basically, we have some distribution and we use it to set the control limits. It's just a matter of what distribution we use. So we have, when the measure that we're monitoring is a proportion, then proportions can be modeled using a binomial distribution, or sometimes a normal approximation to the binomial, but I'm not worried about that. So here's an example of how this works. So we're measuring the percent of customers that were unsatisfied or dissatisfied each month. So they surveyed 200 families, counted how many were dissatisfied, and then turned that into a proportion. Okay, so here's our raw data over here in the right column. Take the average, turns out to be 8%. So in this case, the binomial distribution would have a mean of P, which we're going to say is estimated as 0.08. And then the variance would be P times 1 minus P divided by N. So that would, square root of that would be the standard deviation. And then we would multiply that by however many standard deviations we want to go. So I'm going to say I'm going to go 2 standard deviations plus or minus. We go to our average plus 2 standard deviations takes us up to 0.118, and our average minus 2 standard deviations takes us down to 0.042. So we set up our control chart and we plot our data on the control chart. And now it's a little bit different than the first example we saw. Now there's actually a couple of points that are plotting outside of the control limits. So now this is important, so please listen to this. These control limits are supposed to reflect the natural process variation when things are going properly, things are going well, all right? The fact that we have these points here would indicate to us that something was not going well in month 5, nor in month 11. So we probably wouldn't want to use this control chart because it doesn't reflect the process when it's behaving normally. It includes these points that reflect non-random variation. So what we would want to do is eliminate these points, throw them out of our data set, then using the remaining data, recompute the limits. Didn't I do it? I thought I did it. Recompute the limits, and then they would be much more narrow. Come on. It would be more narrow, but then hopefully they would be reflective of natural process variation. So when you set up these charts, if you get these outliers, you do not want the control limits to be based on those outliers. So you would throw these points out and then recompute the control limits. All right, the third kind of measure is like a continuous measurement, like the diameter of a shaft, or something that's measured in units. And here we typically have two control charts. We use one that monitors the mean or the average, and a second control chart that monitors the variation. So these are a little bit more complicated, but honestly not that much. Okay, so the way it works is it's based on a sample. So every so often we will take a sample. Let's say we're making shafts and we're interested in the diameter of the shaft. So every now and then we'll take a sample of 10 shafts and measure their diameters, right? So from these 10 measurements, we will compute an average and a sample standard deviation, all right? And we're going to plot the average on one control chart, and then we're going to plot the standard deviation on another control chart. Okay. So what distribution do we use? Well, for the average chart, or the central limit theorem tells us that the average should be normally distributed. So we actually know what would be the right distribution to use. We will use the normal distribution to set the control limits. So in this case, I'm going to do plus or minus 3 standard deviations, right? But we would just have a control chart with the center line of the average over all of our data points and plus or minus 3 sigma. We'll show some Excel examples in a minute. And then the other chart is we're monitoring variation. So we're monitoring the mean, right? So the mean, maybe jumping around a little bit, but it should be staying fairly steady. If it were to jump way up or way down outside the control limits, that would indicate a problem that's affecting the mean of the process. Similarly, we want to monitor the variation. So every time we take 10 samples, we compute the sample standard deviation, and then we plot that on a control chart and see if the variation is changing at all over time. So now is a good time to stop and go to our examples. All right, so these are posted and they'll help you with the homework, right? But here we have some quality measure. It's a proportion out of 100 customers surveyed that are not satisfied over time. Okay, so I just took the average of the data. See that right here. And then I computed the standard deviation by the square root of p times 1 minus p divided by n. N is 100 because that's the sample size, 100 customers. And then I just computed plus or minus 3 standard deviations. So it gave me an upper control limit, the red line here, a lower control limit, the red line here. And then I plotted the data on the P chart. All the data plots within the control limits. So this is probably what we would do, how we would have our chart set up. And then we'd monitor out into the future data points. And then if we ever saw one jump way up above the control limits, we'd say, aha, something's wrong. What's going on? Let's find the problem and fix it. In this particular case, the proportion is proportion of customers that were not satisfied. If we ever saw it jump below the lower control limit, that would actually be perhaps indicative of something good is happening, which you probably would also want to find out. Next example is our C chart. So we have a number of defects per unit. So it's a count type data. So I just took the average of our column B data. So that means our estimate of the mean is 5.42, means our estimate of the variance is also 5.42. take the square root to get the standard deviation. And then we're going to take the mean plus 3 standard deviations, draw our control limit there. So now we plot the data versus the control limit, and now we can see that indeed something very unnatural is happening. If you actually look at the data, you can actually almost see it in the data here, how at the very end, clearly something has happened. We're seeing way more defects per unit than we would expect. So what would we do here? We would throw away these data points and then recompute the control limits. So now we have a new average, new control limits. And now it looks more like what it should look like, right? This line is kind of delineating the upper limit of natural process variation. This clearly is unnatural process variation, representing something we would want to detect and figure out what happened. Finally, our last one. Okay, so in this example, okay, I'm taking 5 samples of something. You can stick with our average, the diameter of the shaft or something. So every so often I take a sample of size 5, and I use these 5 data points to calculate the average and the standard deviation, all right? So that's one sample. I collect samples over time. And the first thing I do is I plot the average on an X bar chart. And then the second thing I'm going to do eventually is I'm going to plot standard deviation on what's called an S chart. Okay, so the first thing I did is I set up my X bar chart. So I found the average of these averages, right? I found the standard deviation of those averages. Actually, I took these and averaged them. And then I divided by the sample size, because standard deviation of an average is sigma over the square root of n. So this is what I'm using to, I'm going to go plus or minus 3 of these standard deviations. Okay, so I draw my control limits, plus 3 sigma minus 3 sigma. And I see that I've got a period of time here where something goofy is going on. So again, I would throw out those data points. In fact, here they are in my data. So I would get rid of those. Then I would recalculate the control limits, right? And then I would have my chart ready to go to monitor into the future. All right, so calculating the control limits for the standard deviation, it's a little bit more statistically questionable. We're going to assume that the sample standard deviations, these guys here, these S's, can be modeled by a chi-square distribution. Like I said, that is a little bit more statistically questionable. For them to be chi-squared, technically the distribution of the original data points should be normal. And that's not something we necessarily know to be true, but it often is. So here we would need to get percentiles of the chi-squared distribution. So I'm going to get the 95th percentile of the chi-squared distribution and the first percentile of the chi-squared distribution. So I'm using the chi-inverse Excel formula here. So as long as you have these examples, I mean, you should be able to just kind of, you know, do what I did. Okay. So then, we basically use those to set up the control limits. Wait a second. These are the formulas we use for the upper and lower limits. So we take that chi-squared percentile, the one we got out of, from the chi-squared distribution, multiply by sigma squared, divide by n, and take the square root. And that's kind of like the 99th percentile we expect for our measure. And the same for the lower limit, we use the first percentile. So now we have our chart here. It looks like there were a couple of data points that are well outside the expected variation. These two right here. So I would eliminate them. And replot the control chart. Now here you can actually look at it. And you can see we have some unusual points here. We have a negative value here. I mean, that might be a data error, kind of recording error. Here we have a value 16. Well, that's not. At any rate, we had high variation there. We'd eliminate those 2 points, recompute the control limits, and go again. All right, so basically the homework is I give you sets of data and you go through this process of setting up control charts, plotting the limits. And if you see something like this, you have to eliminate those points, go back and do it again until you have a control chart set up. So, I mean, that's basically it. That's not it. All right, so basically to finish off, the idea of statistical process control is you monitor the process using these control charts. You detect the presence of non-natural, non-random variation. This means that something must be wrong, so you try and figure out what's wrong and you fix it and stop it from happening again. That's what SPC is. It's reactive in nature, right? We're not proactively trying to improve our processes, trying to do it in a reactive way. If you study more about engineering quality, there are more proactive ways that people have proposed to improve processes as well. Okay, that is a long lecture, but thankfully it is now over. All right, next week we'll talk about something I find much more interesting, combinatorial optimization and scheduling. I will ask if anyone has any questions, and when we're done, Sachil will send you to the breakout rooms so you can discuss your team decisions and such. And that will be it. Does anyone have any questions? What's the final count? 41. That's not too bad. I'm not seeing any questions.